Hi and welcome to Lecture 6. In this lecture, we're going to talk about analysis of covariance. So we're going to learn what Ancova is today. To get there, though, we need to start with a simple example as always. So here's what we'll do today. Let's consider that we have some quiz scores. We're going to denote those Y. I'll show you why in a second. For some students in a statistics class. And they are randomly assigned to one of two types of instruction. So let's reveal what those types are and what the data look like. So group one is a traditional lecture class, whatever that means, it's what it is. And the scores of those 6 students are as follows: 5, 6, 7, 7, 8, and 9. Overall, the mean of those scores is 7. So these students score like a 7 out of 10 on average. Group 2 is a little bit different structure. It is consisting of small group tutorials, same class, but just different method of instruction. And those scores you can see here, their mean is 8. And of course, this is the classic type of thing that we expect in this course. We ask the question, are these different? Now, these are the group means that we're interested in. Since we have 2 different group means, we could do a t-test on this. We could also do an analysis of variance. We're actually going to do both here. And in fact, I took the liberty before this lecture of just computing those results, and they are as follows. The answer is no. They are not significantly different. You can do a t-test on that. You get a pretty small t-score. You can do an analysis of variance with just the 2 groups, and you get a small F-score as well. And remember, from what we've discovered so far this semester, that this squared actually equals that. So that's kind of a nice thing. They both result in the following inferential statistics. You can, from the frequentist side, you can say the p-value is around 31%. So we certainly do not reject the null hypothesis, meaning that we cannot conclude that they are different. And there's actually slight support for the null hypothesis if we look at the Bayes factor that comes from that t-test. The data are 1.5 times more likely under the null than they are the alternative. So point is, we did this grand experiment trying to test these 2 different types of instruction, and we did not see a difference, even though maybe we had expected one. So what to do? Well, there's some things that we're not considering here. So, right now it looks like instruction type doesn't matter. But let's look at some other data that we might have. Let's consider also that we recorded pre-instruction aptitude scores, and we're going to call those X for each of our participants. So I put those in red. You can see the exact same data table as before, but now I've overlaid the aptitude scores for group 1 and group 2. And you can immediately see something striking here. You can see that these 2 groups do not have the same mean aptitude score. In fact, group 2 has a lower aptitude score than group 1. So the question is that possibly messing with my results? Forgive the informal way of talking about that. I will make it more formal what we mean by messing with the scores momentarily. Okay. So as I just mentioned, clearly these groups are not equivalent in terms of aptitude. So what if we could also account for these aptitude scores in our analysis? Now, the previous analysis, where we revealed no differences, were simply based on the quiz scores themselves. We were not taking these aptitude scores into account. So can we account for them? And if so, how would we do so? Well, that's the point of today. That is, what I want to know is, how would the effect of instruction type change if we could somehow magically make both groups have equivalent aptitude? In other words, what if we could statistically control for aptitude, remove the fact that these 2 groups come at the course with different levels of aptitude for statistics? Well, it's really cool how we can do that. And I want to show you how that works in the next few slides. So here's how basically we do it. We're going to first fit parallel regression lines to each group. Now, what exactly do I mean by that? Well, you'll see in just a second. And then we're going to use the slopes of those lines to calculate some adjusted means. So if you don't know what a regression line is, that's okay. You're about to see one. That's really the only level of knowledge you need about that at this point. But to demonstrate all of this, I want to just look at the quiz scores plotted on the y-axis and the aptitude scores plotted on the x-axis. And I have made these two groups in different colors. Honestly, I can't remember which one's which here. Let's see. I believe it is the first group, the traditional lecture, that is the blue dots, and the second group, the small group instruction, are the red dots. Let's just confirm that real quickly. Yes, that is the case. Okay, so let's put in a marker just to be clear here. I'm going to put it right down here. These are the traditional lecture, and these are the small groups. Okay, cool. Now we've got a key for our graph. Always make a key on your graph, and for some reason I didn't do that here. So here's a scatter plot. Okay. Now the first thing that I want to show you is if we just ignored aptitude and just computed the mean quiz score for the red group and for the blue group, we could do that and it would look like this. Okay. So for the red group, you see that the mean would be equal to 8. So I'm just denoting that by that little horizontal line going across there. The fact that it hits the y-axis at 8 means that's the mean of the group. Okay, that's no surprise. We saw that earlier. The mean of the blue group, oops, I made it go away all of a sudden. You'll see it again in just a second. The mean of the lecture group is 7. Okay, so 8 versus 7, and we just showed that is not a statistically significant difference. You can see why in this picture. I mean, these things are just all over the place. Most of the differences we're seeing seem to just be noise. Now, what we're going to do in order to do this magical notion of statistical control is we're going to say, there seems to be a relationship between aptitude and quiz scores. Namely, as aptitude goes up, so does quiz scores. If we could do that separately and quantify that relationship for each of these groups, maybe we could use those relationships to get adjusted means. Rather than just 7 versus 8, maybe we would be able to sort of spread that out a little bit. So here's what we do. I'm going to do this with my pointer first, and then I'm going to reveal what the regression lines look like. A regression line, remember, is just a line of best fit. So if we were able to take, say, these blue dots and come up with a line that sort of fit best through them, maybe something like this, and do the same thing with the red dots and make sure that these two lines are parallel, then that would give us an interesting picture. Let's take a look at that picture. And there it is. So this is what happens when we do this thing that I mentioned up here, when we fit these parallel regression lines and then use to each group. Now, what we can do is we can use the slopes to calculate the adjusted means. What do I mean by this? Well, if, and I'm going to show you exactly how this works in just a second, but if we found the mean overall of these aptitude scores, which turns out to be 5. Okay? If we look at this blue parallel line here and this red parallel line here, these two are the adjusted means. And you can see what happens is that we have expanded the difference or the effect of the instruction type. Before is just this, it was 1 unit. Here it is now a little over 2 units in terms of that quiz score. So that's intuitively what procedure we're about to describe. We're essentially putting aptitude into the model as well as the name of the group. And this is what's called an analysis of covariance. So let's see how this works. Okay. Basically, just to summarize what we were saying, the effect after controlling for aptitude is this vertical distance between the regression lines. And we note that it is larger than the original effect, which is just this small distance. Okay. It's kind of a magical thing, and what I'm going to show you today is figure out actually how to compute this distance right here, how to compute that adjusted effect after controlling for what's called this covariate of aptitude. So let's calculate the adjusted group means. How does it work? Well, there's a formula for it. It turns out that all you need to get an adjusted group mean, which I'm going to denote as y bar prime, okay? The subscript j just indexes which group we're talking about. I'll make that concrete with our example in a second. Well, what we do is we take the original group mean and then we subtract some stuff off. And what is this stuff? Well, beta is the slope of those regression lines. Okay, and I'm going to tell you what it is in a second, but I'll show you in JASP how to find it momentarily. And then the thing we multiply here, this is the mean of the covariate scores, so the mean aptitude scores for the group minus the overall mean of the covariate scores. So this is why it's important that you know which variables represent y. These are your primary outcome, like the quiz in this example, and you know which variables represent your covariate, that is aptitude in this case. So that's the formula. You'll want to write that down somewhere. Let's actually apply it to calculate some adjusted means. So remember, the story is the mean quiz score for the small groups was, oh gosh, what was it again? Let's go back up to the picture. It was 8, and the mean quiz score for the lecture was 7. Not much difference between them. Well, let's adjust and let's figure out how big those differences are now once we've taken into account the aptitude scores themselves. So for our data, group 1, the traditional lecture, would be this way. The adjusted group mean for group 1 is the mean of group 1 minus beta times the aptitude mean for group 1 minus the overall aptitude score mean. So what are those numbers? Well, some of them we already know. Certainly the traditional lecture mean was 7. The 0.706, that is the slope of that regression line. Now, just take that for granted right now. In a few minutes, I'll show you how to get it in JASP. And then the mean of the covariate score, so the mean aptitude score for group 1 was 6. And the overall mean, which we didn't look at before, well, it's just the mean of 6 and 4, which is 5. So we were able to find that. Once we do this arithmetic, this gives us an adjusted group mean for the traditional lecture group of 6.29. Okay. Now we do the same thing. This doesn't really make sense unless we do it in comparison with the other groups. So let's do that. Group 2, the formula works the same. I just put a 2 everywhere. And let's do that. So the group mean for the original group mean for group number 2 was 8. Okay. Slope is still 0.706 because those lines are parallel. But the covariate mean, so the aptitude scores for group 2 was 4 minus the overall mean of 5. And we do that arithmetic, and we get an adjusted group mean of 8.70. So now what's happening is we're getting 2 adjusted group means that are farther apart. In fact, the difference between these is about 2.4. So you might wonder, are those different from each other? Well, that difference of 2.4 is exactly this vertical distance that I just showed up a second ago. It's this distance between here and here. And in fact, those adjusted group means are exactly at these heights over the overall aptitude mean. So there's a lot going on here geometrically, but in the end, what we're doing is calculating these adjusted group means. Now let's make a couple of notes about this. First of all, these, as I just said, these adjusted group means are farther apart. Okay, so that's good. What's going on here is that the adjustment procedure literally removes the effect of aptitude. Look at what the formula is doing. It's saying take the original group mean and subtract some stuff off. What you're subtracting off is the effect of aptitude for that group. Okay, that's why the mathematics there looks like it's why it has that slope for the regression lines. It's the continuous effect of aptitude. Okay, so analysis of covariance, which is what this is called, literally is you adjust the group means by removing the effect of some covariate. Okay, remember that. That's what makes analysis of covariance work. So let's talk about how to do it in JASP. I'm going to give you some steps that we're going to cover first, just so that you have them in your notes, and then we'll go into JASP. I've got it ready to go, as you can see here. We'll go into JASP and actually do it. So the first step when doing an Ancova is actually not to do an Ancova, or analysis of covariance. It's to do an Anova first, because if you don't need to include the covariate, then don't, right? There's no reason to make things more complicated. So typically we perform the Anova as a function of some group variable. So in this case, that's the instruction type. Now the next step is if we want to follow up on that and consider what happens when we add this covariate into our analysis. Well, the first thing that we do is we perform a linear regression on those y variables with x, the covariate, and the grouping variable as covariates. Okay, not just x itself, but with both x and the grouping variable. Now what this is going to do is it's going to give you the slope, that is the covariate effect that we need to calculate those adjusted means. So when we go back up here to this example, and I told you about this 0.706, this comes from this procedure of doing the linear regression and finding the slope. So you're going to see that pop out in JASP here in a few minutes. And then once you do that, oh, by the way, you're going to use something called the unstandardized coefficient. I'll point that out in just a moment. And then once you've done that, you can then perform the Ancova. And that's going to tell you, okay, once you've adjusted these means and you've accounted for the influence of that covariate, are the differences different now? And today we're going to focus on using just the frequentist paradigm. So we're going to talk about significant differences and use p-values. The next lecture we'll do Bayesian Ancova, but I want to save that for just one lecture itself. Okay. So that's what we're going to do. After we do this, we're going to learn how to write the results. So let's go to JASP and let's do these 3 steps. Okay. So here is the data file in JASP. Now all I did was put it in the same format as we would have done last week. That is, I put the dependent variable of quiz down all in one column like this, and then I made a grouping variable for instruction type. And I put numbers in, 1 for traditional lecture and 2 for small group. A small technical note here, if you're making your own data file, to do analysis of covariance in the way that I've described, you have to make your grouping variable, you have to make it numeric. Okay. The reason is because, as you'll see in a minute, the linear regression won't work if all you have are labels here. So even though in the last video we used verbal labels, and I encouraged you to do so, for this procedure specifically, you'll really want to use numeric labels. So 1 and 2 is just fine. Some people use 0 and 1. There's some good reasons for that, but 1 and 2 will be fine for what we're doing. Now I've got the quiz scores, and I've also got the aptitude scores in there. So here's what we're going to do. We're going to first, we're going to assume that we've done the Ancova already. In fact, I reported the Ancova at the early beginning of this lecture. You know how to do that. You just go to Ancova and click Ancova. Let's assume we've done that, and now we want to explore the effect of the covariate. So the step that we're going to do is we're going to perform a linear regression on these quiz scores with the instruction type and the covariate as predictors or as covariates. So the way we do that is this. We go to regression, and we're going to go under classical and do linear regression. Okay. Now we're going to stick the dependent variable in this box. The dependent variable is quiz. Okay, and there it is. And we're going to put the covariates in this box. So we'll put instruction type. Oh, it's not working. Why is it not working? Well, one of the things that you might notice is down here in the box, this tells you what is admissible as a variable type. And this little ruler means it needs to be a variable that is a scale variable or a continuous variable. And you'll notice that instruction type is actually listed as a nominal or grouping category variable in JASP right now. What I actually need to do for this step, and for this step alone, is I need to go to the data itself and change the variable types all to scale. Okay, that's going to make things make sense for the linear regression. And then we're actually going to go back and change it in a second to do the Ancova. But for the linear regression step, we need to make sure that these are all scale variables. Now we go back to the linear regression. We're going to put quiz score as our dependent variable, and then we'll put the grouping variable and the covariate both as covariates in the box. And that's it. I'm going to skip that over here. And now what we're looking for is one thing. We're looking for the, quote, effect of the covariate, the effect of aptitude. And what that's going to be is the slope on the aptitude term in the model. So what I need to go down here is, what I need to find is the box labeled coefficients. That's this one right here. And then I look at the H1 model, and you'll see there's 3 different coefficients. There's an intercept, an effect of instruction type, and an effect of aptitude. This is the one I want right here. It's the unstandardized coefficient for the covariate for aptitude. And then you've seen this number. It's 0.706. That's where that 0.706 in the previous calculation came from. Remember that? Let me just pop back there real quick. It's that one right there. Okay, that's where it came from. Okay, so we do that. And then the next step, and this is the last step, is we can use that to then compute those adjusted means. We did that just a little bit ago. And now we can go back and do the actual Ancova. So here's what we do. We go to the Ancova button and we select Ancova under classical. And this will look very similar to the Ancova menu that you've used before. It's just this time it has a box for covariates. So at this point, there's something that we need to do. Notice in the fixed factors, those have to be either categorical or nominal. So we need to go back and fix our instruction type variable. We need to change this back to nominal. Okay, we can keep these as scale. That'll be just fine. Now, once we've done that, we can put quiz in for the dependent variable. We can put that fixed factor of instruction type. In fact, when you do that, you'll see that you get exactly the results in the Ancova over here that we reported earlier. Okay. But then we want to also account for aptitude. We're going to put that in the covariate box. And then once we do that and look at the table that results, look at what we have. The effective instruction type now has a much bigger F ratio, and as a result, a very, very small p-value. Because what has happened is all this variance, aptitude is actually accounting for a lot of that leftover variance. And so at this point, we've got a significant effective instruction type. So what we did is we statistically quantified this picture that we were looking at earlier, which is right here. If you somehow account for the effect of aptitude on scores, i.e. these lines here, these linear relationships that we're seeing, then you can actually adjust the means farther apart. They are farther apart than what the actual raw data seems to indicate. Seems magical, but it's absolutely solid mathematics that's going on here. You're simply entering another term into the model to account for some of the residual variance. And when you do that, what's left over is, in this case, a significant effect, a significant difference. So let me go down to show you how we're going to take all this information and write it up. So this is what's important about these things now. It's not only how to do it, but how to actually communicate it. So here's how to write the results. We'll take it a part at a time. The first part that we'll do is the first step. We're going to talk about what we did. We performed a one-way Ancova on the final quiz scores as a function of instruction type. Right? That was the first thing we did, and what we discovered about that is that the mean quiz scores were not significantly different between the traditional lecture, which had a mean of 7, and the small group tutorial instruction, which had a mean of 8. And then after that, of course, we write the statistics that tell us, that back up that statement. So there's the Ancova and what we found. And then at that point, we do the Ancova as a follow-up, right? So we're basically saying, but aptitude's in there, so maybe that's explaining some of these differences. And if we get rid of that, maybe the actual true group differences will pop out. And that's what happens, and let's write that up. So however, when we accounted for the pre-instruction aptitude scores as a predictor in our model, the difference between the adjusted mean scores, and I'm going to highlight this because that's an important word that has to be there. The difference between the adjusted mean scores was increased. And in parentheses, I say that it was 6.29 for the traditional lecture compared to 8.70 for the small groups. So you can see we took a difference of 7 versus 8 out and expanded it to a difference of 6.29 versus 8.70. Okay, that's the part where we computed the adjusted mean scores. Now we need to back that up statistically. So this is the Ancova. This difference in covariate adjusted group means was statistically significant as confirmed by an Ancova, including aptitude as a covariate, comma, and then I write the results. You might notice that the degrees of freedom here was 10 up above, right? And now it's only 9. That's because you've entered another term in your model, and thus you've lost a degree of freedom within the groups. Okay, but in the end, we have a nice significant difference. So that's all I wanted to do in this video, was to introduce you to the process of Ancova. Ancova is sometimes referred to as statistically controlling for other variables that might be influencing your mean scores. So there's lots of things to do with Ancova. Ancova does not always work out the way that we're demonstrating here. In fact, in our practice sessions this semester, we will see that you can actually have all kinds of outcomes after performing an Ancova. But this is kind of the classic way of looking at it. You take something that's not different, and then you, after accounting for an Ancova, show that, yeah, it actually is different after all. And of course, that's nothing more than this picture that we said earlier. Okay, so it has a nice geometric flavor to it as well. Okay, so that's all for now. Next time we'll look at Ancova from the Bayesian perspective, but for now I want you to know what it is geometrically and how to actually compute those adjusted means. Oh, and I'll mention real quickly, if you're in JASP, don't say this too loud, if you're in JASP, there is actually a way to find the adjusted means down here buried in one of these menus. I'm not going to tell you what it is right now though. You play with it. And if you do find it, please only use it to confirm your actual hand calculations, because it's the point is to learn how these hand calculations work so that you can better understand the underlying models. Okay, but that's a nice little challenge for you guys. Okay, so that's all, and I will see you on the next video.